in this section, I want to cover functions, mathematical functions, looking at 1D, 2D, all the way up to 5 dimensions. And then also to distinguish between the continuous domain in time and space, as well as the discrete domain. And it's the discrete domain that we'll be focusing a lot. So we really need to get a clear grasp of that. So functions, as I've said, they can be many dimensions, 1D, 2D, and so on. And the number of dimensions is referring to the number of independent variables in what's called the domain of the function. So here are some examples on this slide. We've got mountain height h is the height, as a function of the position variable x. Okay, so this is like tracing out the profile of a mountain, which gives us an example of a one-dimensional continuous function, height h as a function of position x, where x here is any real number, any real number from minus infinity through to plus infinity. Another example would be just looking at the height of a stone that is thrown into the air. And so here this is tracking the height of the stone, h, and showing how that varies with the time variable t. So hopefully the concept of a 1D function is straightforward. Building up now to 2-dimensional functions, staying again with the example of a mountain. Here we now have the mountain height h as a function not only of x now, position variable x, but also the position variable y. And so this is actually producing this kind of surface plot, giving us the height h as a function of position xy. And we could show that as some kind of surface, some kind of, literally like a mountain range viewed from above, and you'd see the kind of the surface features. Or we could represent the height h as a grayscale value and plot that same function in this way here. Still the same function, just shown in a different way. So here we've got x and y, and now some grayscale value where white means high and darker grey values mean low mountain heights. And that again is represented here in this top right corner where we're showing the x and y coordinates explicitly and then showing that we've got some response, some measurement h. We're measuring the height as a function of those two independent variables. And so you may see it also written in this kind of way. We're saying that we've got the height h as a function of a vector position r, where that position r is just composed of two real numbers, okay? So it could be anywhere on the x-axis, real numbers running from minus infinity to plus infinity, and then the y-axis running from minus infinity to plus infinity. And so we can often show a vector as just a list of numbers, and in this case, we've only got two numbers for the two independent variables, and so we just have x and y in this column vector. So an MR image is another example of a 2D function where we've got the x-axis, y-axis, and now we've got some kind of grayscale value representing the values that are being measured in MR, and that's typically the net transverse magnetization that gives us this MR image. Building up complexity further, we could now consider a 3-dimensional function, such as a 3D PET image. So you could view that like in the top right corner here as a whole series of slices. And here I'm just showing one example 2D slice in x and y. So that's shown here. But of course, it's not just x and y. We also pick the slice, which here is given by a third dimension, the z dimension. And so that's why this is now a 3D function. We have three independent variables, x, y, and z, for which we are getting some grayscale value f, which in the context of PET would represent the concentration of the radio tracer in that position in the brain. And of course, with such images, we can do all kinds of processing. So we could easily just scan along a single line here and draw some kind of profile, a bit like the mountain height example that we just saw. So when we've got a very high dimensional function like this, there's nothing to stop us reducing it to 2D functions or 1D functions, whatever it is that we extract from that function. Another example of a 3D function would be what you're actually watching now, which is a video, or in fact a series of slides. And so you could imagine the series of slides I've been presenting to you. Each of those is a 2D function in x and y, but now the third dimension would be the time or temporal dimension. And so that's why we now get a grayscale value f as a function of x and y and as a function of time t. And so, of course, television, video, all of these are examples of a 3D function. And it's just a question of whether we're looking at black and white grayscale values f, or whether we'd use some kind of color value encoded with red, green, and blue RGB, which would be a 3-element vector as a function of x, y, and t in this example. So here I've got yet a further example from medical imaging. This is a dynamic 2D MR. And so here you're seeing a coronal section through the chest of a patient, and you're seeing that there's respiratory motion here. And so by looking at the image changing with time, that again is giving us a 3D function. So in other words, the coronal section, what it looks like as a function of time t. Going up to 4D now, so that'd be the example of dynamic 3D PET imaging, where now we'd have a whole brain image. So we've got a brain image in a 3D function for each of these different time points. So I'm showing at the bottom left here an XYZ coordinate system for the 3D brain image. And then I'm showing that we could have that as a function of time t. Now, as you can tell in this example, these are discrete cases, but just for the moment at this stage I just want to represent the concept of a 4D function. You know, in principle, in theory, we could have that as a continuous independent time variable, and so we really could have a 3D function which varies continuously with the time variable. Working up to just one last case I'll give, which would be a 5-dimensional function. So here I'm looking at the example of using an MR image to figure out where we are in the respiratory motion of the patient. And so according to the position of where we are in respiratory breathing motion, that will determine where we are on this G, or this gait axis. So what we do here is we just basically group each of those ranges of positions into what's called a gait. And so we'd have a discrete variable G for gait along here. And then once we've kind of frozen the motion for that particular gait, we could still have a 3D PET image, which then still varies with time as well. And so again, I'm very much forced into showing this in a discrete context because it's far easier to visualize. So a 3D image as a function of time and as a function of the breathing position, the gait G. So we haven't been using analytic expressions yet for these functions, but that doesn't mean we can't call them functions. We still will be calling them functions, and we will go into a lot of detail later on about how we describe these relatively complicated functions. But just to acknowledge on this slide that, of course, we are more familiar with analytic expressions for functions. So here we've got classic examples, like we could have a continuous function f of t. This would just be a 1D function, which is, for example, the cosine of time t. Or again, with logarithm of x for p of x, or x squared y of x for y as a function of x. Those are classic analytic expressions. And also, just to show here in 2D, we could have 2D examples. So a continuous function f of x and t, just given by, say, this linear x and then sine of t. These are just arbitrary examples showing you analytic expressions for 2D or 1D functions. But the point to say is that we could still, as we've been seeing, call all of those examples functions, like on the left-hand side there, where we've got some value f as a function of some independent variable. We can still do that. It's just that the right-hand side will be a lot more involved than just one simple analytic expression. And so as I've written at the bottom of the slide here, what we will find is that according to the different problem that we're dealing with, we can actually use summations of these very simple functions. Often we'll be calling them basis functions, building block functions, which we can sum together to represent these relatively complicated signals that we've been dealing with. But that's really, this slide is just to say, yes, normally we have analytic expressions for functions, but that doesn't mean we can't still call these very complicated signals. We are still enabled to call them functions as well, as we will see as we go along. Here I want to point out what I mean by a continuous function. So we say a continuous function, but often what we really mean there is that the independent variable is a continuous variable. In other words, it's got a continuous domain. So to be explicit, we'll be using these kind of rounded brackets for functions. And what that means is whatever the independent variable is inside those rounded brackets will be an independent variable that can vary continuously. So if we had height as a function of time t, then here the t would be a continuous variable. So it'd be an element of the set of real numbers, which vary from -infinity continuously all the way up to +infinity. And that's in contrast to the case we'll be covering next, which is discrete variables, where, for example, that might just now be an integer value, and so cannot take on arbitrary values. And also I'm showing here that we need to be very flexible in our notation. So here I'm pointing out that we may use all kinds of different representations for the function value. It could be height h, it could be an angle theta, it could be a position x that is the function value, or it could be a position y, or it could be some capital T for temperature. So you've just got to look at the what's just in front of those round brackets and understand that that is the function value, and that will depend, and if it's with rounded brackets, that will depend continuously on the variables that are contained inside those round brackets. And again, when it's round brackets, that means those independent variables can continuously vary. So that's why I'm just showing many examples here. And one other point that's really quite important for understanding some of the mathematics that we'll come across later is to understand that if we supply a fixed value for the independent variable, so imagine I just plugged in a value of 10 for t here, then because t is now fixed, that means we're going to get a fixed value h that comes out the other side, if you like. So if we supply a fixed independent variable value, then we're no longer really dealing with a function so much as actually just getting a function evaluated at a fixed point, which is going to give us a constant value. That'd be very useful, and I will talk you through that when we get to examples in the mathematics later, but it's very important to understand that when we're dealing with a full function or when we're dealing with an evaluation of a function at a particular point. So as mentioned, to now be explicit about the discrete case, I'm showing here a continuous function f of t as this kind of continuous line here with the independent variable t. And then I'm showing a discrete function, f of t. And now to give away the fact that t is now a discrete integer variable, I'm either going to use a subscript t instead of the rounded brackets t, or, and this is the case that we'll use a lot in this module, I can use these kind of square brackets, the square parentheses here, to reflect the fact that what's inside, and here what's inside the brackets is time, t, is now to say that that is a discrete independent variable. And so that means here it would only take on integer values. And so to relate that back to the continuous function, we can say, well, it's just some integer value t multiplied by some sampling period ts, which would be the interval between those samples. But don't worry too much about that at the moment, because sampling will be covered much later in the course. Here on this slide, all you really need to grasp is the fact that f as a function of t with the round brackets gives us the continuously varying line, whereas f with the square brackets means that we just have the function f defined at very fixed integer values t. And then at the bottom here, I've just acknowledged the fact that, of course, on computers and in reality, often the function value itself can be discretized. You know, we can't just have arbitrary, really high precision for the function value f. In reality, it's often itself comes in with limited precision, which means it's kind of composed of, if you like, quanta of sort of tiny increments. It can't take on literally any value, but it will be slightly constrained. However, in these lectures, we will consider it as a real value that can take on a value with arbitrarily high precision. And so really, we're just going to distinguish between the discrete time variable t or a continuous time variable t. And of course, what I'm saying here applies just as much for the space coordinate x as it does for time t. So really, this is very similar to the last slide, but just gives you another example of a varying function. This one is x of t. So again, the need for flexibility in notation. That means x is the function value. So that's the, if you like, the vertical value along this function that varies with time t. So that's why I'm calling it a continuous time function. So x of t, where t can take on any real number. And here, this is like a sampled version of that, where we're just showing that now we only have the function value x evaluated at these discrete integer positions, which would run from, could still run from minus infinity to plus infinity, but they're now integer values. So here I'm showing that n is now one of the integers, so an element of this set of integers z. So actually a very straightforward concept, so not too difficult to grasp. And the tip here is just look at the brackets. Okay, if they're round, it's continuous. If they're square, it's discrete. So let's go into some explicit examples of discrete functions. So here we have an example of a stock price, which is an example of a signal. Remembering that can be any measured value. And so here it's just to point out that we now have this stock price P, if you like, P, which varies with time. And you know, here, strictly speaking, because time is in an integer form, for example, day number 1, 2, 3, or 4, we would use the square brackets. But you'll often find that people nonetheless quite loosely use notation such as P round brackets T. So here we're just going the extra mile to be very precise about what is that independent variable. Is it continuous? Is it discrete? But you'll often see people casually using P round brackets T when it's probably a discrete function. But also it's just a list of numbers, so we'll get to that another time where we could just write P as a vector and just say it's just a long list of values. And also the time activity curves, which I've mentioned earlier, can also be regarded as 1D discrete functions. So you can look at these kind of box values here. It's quite a noisy time activity curve. And so really we've just got very discrete choices of the temporal variable, and we're just looking at the response value f. And so you can see here, actually, I've got a rather loose notation, f round brackets t, and so really that should refer to that continuous line, that black line, rather than the discrete measurements. But just to give you another example of a 1D discrete function. Moving on to 2D, there's that mounting height example, which was a continuous function. But of course, we could sample the mounting height at particular positions x and y and end up with a 2D grid of numbers. Okay, so we've got, if you like, we can consider this as integer position x, integer position y, and we've just got a value h evaluated at those positions. This hopefully will make that even clearer. We're going to imagine this is a continuous function. This is a model of fluorodeoxyglucose uptake in the human brain through what's called a transverse section. And so we've got the tracer concentration F varying with X and Y. We could discretize that, and so I'm showing that explicitly with these this pixelated version of the image. And so I'm swapping from the round brackets to the squared brackets, and then showing down here what that function would look like if we were to try and represent it in that continuous domain. But for the moment, just consider this as a set of values of X and Y, discrete values for which we get a function value F. And then I'm showing a very extreme discretization to really prove the point on the right-hand side of the slide. So again, these are very simple concepts, nothing too difficult to grasp. And often you can get away with the informal notation, but let's just try and be explicit when we're referring to discrete or continuous variables. And then just to jump back to that 5D example, which was already discrete. And so that's definitely a discrete function. We've got discrete time bins here. I've just got sort of 6 time values, and I've got 3 different positions of the respiratory motion for which I can kind of freeze the motion at those different gating positions. And then I've got voxels, volume elements. So even the X, Y, and Z is also discretized. And so that's why I've got a function value F, that's the PET radiotracer uptake, which varies as a function of these discrete values, X, Y, Z, time, and gate. So just to wrap up, the summary is, I hope you've now grasped the important concept of the dimensionality of functions. That was the key point to get here, whether it's 1D, 2D, up to 5D. In this Signals and Systems module, we'll be focusing, you may be glad to hear, on just the 1D case. So it will actually be quite simple to understand. We certainly won't be dealing with 3D or 5D. We will use 2D where it's actually helpful to understand the 1D case. And then we reviewed the fact there's a continuous domain where time and space can vary continuously. So often we use the adjectives temporal and spatial when referring to time and space. And then likewise for the discrete domain, we could use then integer values for time and space. And if you're wondering how to relate those to arbitrary values, then again, you can just multiply that integer by some sampling period, and then that will get you from integer values to say 2.5, 5, 7.5, 10 if the sampling period was 2.5. But again, all of those details will be covered later. This really is all about understanding dimensionality, continuous functions, and discrete functions. Thank you.